Back in October, I successfully launched my TBC rocket.
Okay, ready?
Yep.
5, 4, 3, 2, 1.
Let's go!
Oh my god, that was perfect.
Dude, it was perfect! Oh my god! Let's go!
Oh my god. That was awesome.
That was insane! That was insane, dude! Let's go!
Oh my god, that was perfect. Okay, ready?
Yep.
5, 4, 3, 2, 1.
Let's go!
Oh my god, that was perfect.
Dude, it was perfect!
I actually started this project over 3 years ago in 2022. And as you can see in these pictures, my CAD models weren't great. I was actually just learning to use CAD during this time. So that led to March 2023 when I decided to redesign the gimbal. And you can see here, it's a cleaner, more compact design. So I went from a 4-inch diameter gimbal to a 3-inch diameter gimbal, and I moved everything a lot closer to the center. So overall, it was a lot cleaner. I then ran 2 tests, one for each servo, to find the relationship between servo position and the resulting motor mount angle. I wrote a simple script that moves the gimbal back and forth with the IMU mounted on top of it to measure its position. I used the data from these tests to produce these graphs. The graphs show a roughly linear relationship between servo position and motor mount angle. These slopes describe the difference in motor mount position required for every degree of motor mount actuation. These numbers were later used in the code to take a desired motor mount position and calculate the desired servo angle in order to get that position. I then developed the CO2 ejection system, which I've talked about in a different video, so I'd recommend watching that. The design at the time looked something like this. In November 2023, I attempted my first launch. However, the motor was unable to produce enough thrust and the rocket failed to lift off the pad. But there were actually a few other problems which I would later find out about. So first of all, data from the IMU would occasionally freeze or give repeated values. When it's supposed to update 1,000 times every second, it would just give me the same values for every cycle. Second, the servo motor sometimes twitched or vibrated. I couldn't really find a great visual of this, but I found this video from 2 years ago, and you can see the servo motor twitch a little bit. You can actually hear it. It was also extremely difficult and time-consuming to set up. The rocket had 3 separate components: the ejection system, the avionics bay, and the gimbal, which all had to be placed separately inside the engine and aligned perfectly with these screw holes that were in the body tube. So it would take me at least 10 minutes every time. So everything I've talked about so far, from designing the gimbal to the first launch attempt, that all happened in my freshman year, the summer after my freshman year, and part of my sophomore year. But once I got into my sophomore year, I found it incredibly difficult to find any time to work on this project. So I took a break basically of 1.5 years until 2025. The first one of these problems I addressed was the freezing data problem. So it was actually a pretty simple solution. What happened was when I would set up the rocket, I would always flip the IMU upside down like this, and that would just cause the data to freeze for some reason. It sounds pretty stupid too, but it was actually because of how difficult it was to set up the rocket. I would have to flip the whole thing upside down every time to put the avionics bay inside the rocket. Originally, I assumed that the servo twitch was caused by inconsistent voltages, but this was actually not the case. It was actually caused by communications with the IMU, which were interfering with PWM signals being sent across digital pins. This was also a fairly simple fix that just required the servo driver from Adafruit. Making the rocket easier to set up was also a pretty simple fix, which required designing this internal structure that connected all three components inside. Instead of having to screw in every component, we can just put everything together before we put the rocket together and then slide the whole assembly inside. This included designing these alignment rings. So how this works is this male ring goes on top of the internal structure, and then when we slide it inside the rocket, it aligns with this female ring, and they snap together like that. So that way we can get consistent placements of the internal structure, and we can find the screw holes really easily. I also made this little cutout in the body tube so the avionics are accessible from the outside. Now the most important thing I haven't talked about is the code. So I'm not going to get into too much detail on the code, but the most important part of the code is the PID controller. So how do we take a measured position and use that to get a desired servo position? For those of you who don't know, PID stands for proportional, integral, and derivative. So with proportional, you take the raw position and multiply it by a certain number to get another number. With integral, you take the position added up over a period of time, and then you multiply that by a number. And derivative, you take the instantaneous rate of change of the position at that point in time, and then you multiply it by a number. Then you take those three numbers and add them together to get one position. I ran a series of 7 propeller tests to simulate the rocket's thrust. After every test, I would graph the data, and based off of that, I would adjust the PID gains for the next test. The prop testing method isn't perfect because important factors like mass or moment of inertia are going to be a little bit different for a launch situation versus the testing situation. At this point, I was already close to producing a stable test, so I just decided to move forward with the full launch. I wasn't expecting a stable first launch, but I knew that a real launch would give me better data than prop testing.
3, 2, 1.
So the rocket actually flew straight, which I was not at all expecting on the maiden flight. But there was one little problem. Pretty much everything broke on impact. So obviously the CO2 parachute ejection system didn't really work the way it was supposed to. The cartridge was punctured, it just didn't produce enough force. I did have a theory for this. It was a fairly chilly day, which can have a significant effect on a CO2 cartridge. So I tested this by firing off a CO2 cartridge at whatever temperature it was already at, and firing off a different CO2 cartridge after it had been placed in hot water. As you can see, this made a huge difference. So just keep this in mind if you ever use a CO2 ejection system. As for this rocket, I'll be switching to a black powder ejection charge. I wanted to avoid this at first because I didn't want any flames to be right next to my electronics, but ultimately it's going to cut down a lot on the weight. Now let's look at the data. This graph right here shows the raw pitch and yaw values from liftoff to motor burnout, as well as pitch position and yaw position, which are the respective servo motor positions. This graph right here is a better visual in my opinion because it shows absolute error, which is pitch and yaw squared, added together, and then square rooted. So basically the Pythagorean theorem. As you can see, the rocket's error stayed below 10 degrees the entire flight. This graph right here shows the integral of pitch and yaw, which, and I just learned this, is called absiment. The integral of position is called absiment for my physics nerds out there. These last two graphs show something pretty interesting. The rocket was in a controlled offset position for almost the entire duration of the flight. You can see that in this video. Although the rocket flies mostly straight up, it also flies away from the camera and lands maybe 50 feet away. Now, I'm pretty sure this has to do with the CO2 ejection system because as you can see, it's off center because I had to make room for the servo right here. So therefore the mass is off center and the rocket flies in that direction. This graph shows vertical acceleration from liftoff to impact. You can see this spike here, which is the CO2 ejection system firing off. What's cool about this graph is you can integrate it and get vertical velocity and integrate that and get altitude. Moving forward, the next step will be a second launch to validate the new ejection system. Also, you may have seen how messy the avionics bay is, so the plan is to eventually move on to a PCB. I'm having one of my friends design it, but it's kind of taking a while. And then ultimately, I want to launch on longer burning motors, so ST's E12, and then ultimately Aerotech G12, which burns for, I think, 12 seconds. So see you soon.